go to infinity. And then you want to compute the gravitational field, h mu nu, at a certain point tx in space-time. And what we explained yesterday was each component of h mu nu satisfy an equation of this type. In linearized gravity, on the right-hand side, you have only the stress energy tensor of matter. And you solve this equation by using the retarded Green's function, which means you can write h mu nu as a certain retarded potential, which is an integral over the source. But then what you want is to expand it in multiples. And multiples for tensor fields means, as we explained, irreducible representation of the group of rotation. Those look always like big words, but I will explain in simple terms what it means. At the end, and by the way, this thing was done correctly for the first time only in 1991 by Bala, Ayer, and myself, okay? Before, there were previous attempts that were not correct. So the final result is the following. You have the source in Einstein's equations. It is very convenient to introduce a kind of matter density, sigma, which is not, as you would expect from E equal mc squared, you know, T00, the energy density. But for many reasons, it has to be T00 plus the trace of the spatial part of T mu nu, which means in cosmology rho plus 3p, because in some of the Friedmann equations, indeed, it is rho plus 3p, 3 times the pressure, which is very important. In inflation, for instance, it's very important that p being minus rho plus 3p is negative. So for some versions of Einstein's equations, this is the important density, which is like energy. Anyway, it's a notation here. You just call it sigma. The other component, you just give names, T0i, I up being called sigma I. The indices on the left, they are moved by the spatial, the Euclidean metric, so I don't care if they are up or down, okay? And sigma ij. Now, the end result is that all the components of the metric can be written in terms of 2 infinite sequences of multiple moments which are time dependent. And these multiple moments, they are explicitly written here. There are some integrals over the source, because you see these are integrals that contain sigma or sigma with 1 index or sigma with 2 indices with some derivative of the source. Then we recognize in this first term, this is the usual multiple moment if you have a matter density rho. Yesterday we explained the usual multiple moments. This is rho x, 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 symmetric trace free. It's the usual Newtonian multiple moment of a mass density. In general relativity, you need to complete this by terms coming from the momentum density and the stress density. And you also need to do an average over the time variable that you introduce a fluctuation, let us say, of the retarded time u equal t minus r by a quantity plus or minus r over z, and you integrate over this. The reason being that when you do a multiple expansion, you are cutting, you are at each region here, you are cutting the retarded potential depends on a certain cut of the source. But if you do a multiple expansion, this cut goes around. At the end of the formalism, it comes to this delta L, which is a function of z. This function of z is a function which is called delta L because it looks like this. Okay, when L is very large, it becomes a delta function. This is just it's not important, those details. What is important is the metric is written in terms of those blocks. Okay, the multiple moments. There are 2 infinite sequences of multiple moments. The multiple moments of the mass type called IL, let me remind you that L is a notation for L indices. Each index goes from 1 to 3, and all in these things are symmetric trace-free, okay? So it's a short notation for this. The first list of multiple moments, they start with L equals 0. For L equals 0, this thing actually, when you look at it, you find it is the total mass of the source, okay? So I without any index is the mass of the source. I with one index is the dipole moment of the source in a relativistic sense. And then starting with two indices, this is a quadrupole, etc. So these are quadrupole mass type multiple moments of the even parity type things. And the other moments, J, they start at L equal 1. And the first moment, Ji, you can recognize here epsilon with three indices is the Levi-Civita symbol, so-called, which is antisymmetric in three indices, although it was used by Ricci before Levi-Civita became a student of Ricci, but the big cat gets all the milk. So as you can see this is X cross the momentum density, so X cross P, so it is the angular momentum. So the J with one index, that's why it's called Ji, it is the angular momentum of the source. And then you have the quadrupolar type angular momentum, okay, with extra indices, okay. So the theorem is essentially because, yes, yesterday we said for a scalar field, I have one infinite sequence of multiple moments, okay, all of the same type. For any other massless spin field, spin 1, like electromagnetism, spin 2, you have two infinite sequences, okay, of even parity and odd parity. The reason why you have two is there are two transverse degrees of freedom in 3+1 dimensions, so at the end, that's why there are two. And there are also gauge terms here. That is, this is the general solution outside the source expressed in terms of the source, modulo a coordinate transformation, which I did not write here. Each block here, you can see, because this is the interest of using, usually in textbooks, you will write this in terms of Fourier transform and the Bessel functions, and then you don't see exactly, in my opinion, why it is true, okay? Why here, this is a function of u divided by r with many derivatives in front. Evidently, this is a solution of D'Alembert equals 0, because this is a solution of D'Alembert equals 0. This is a solution of D'Alembert equals 0. Here there are two derivatives. This is another solution of D'Alembert equals 0. And same thing for the J part, okay? So it is clear that we have decomposed the metric here in solutions of D'Alembert equals 0. And it is also clear that the building block here is an I with L indices. Here it is the time derivative of this tensor with also L indices, because the notation L minus 1 means a succession of L minus 1 indices, okay, which means I have one less, and you add one, so it means there are L indices in all, okay? And when you make a rotation of the source, now under a rotation of the source, the multiple moments will rotate, okay? But by definition, this is what is called symmetric trace. I mean, it's an irreducible representation. They go around each other, and therefore each one of these blocks is multipolar in the good sense. And just the last remark, although it's traditional to call these things L, actually, in the sense of quantum mechanics, this should be called J. You know that in quantum mechanics, you say that J equal L plus S. Now I'm in quantum mechanics. The total angular momentum of the system is the sum of the orbital and the spin. And this L is really a J, because what would be the orbital thing would be the fact that I have derivative with respect to the angles here. So the number of derivative would be the orbital part, but at the end, what counts is the is the fact that this rotates in a certain 2L plus 1 dimensional representation of when I do a rotation. Okay? So now this is linearized gravity. And although, in a sense, this is simple, it was done correctly only in 1991. And the final thing is, this is the solution everywhere outside the source. Now, if I go very far from the source, I will see the gravitational wave. How do you do that? To get the gravitational wave, for instance, you look at all those things. A term like this is a derivative. Let's say, let me consider the one, let me consider, okay, this term to start with. This term contains, if L equal to, two derivatives, and then IIL, IIJ of U, which is T minus R over R. Now, if I do explicitly the derivative, what will happen? I must differentiate either the R which is here or the R which is here. If I differentiate the R which is here, it will become 1 over R squared, and therefore it will decay like 1 over R squared, 1 over R cubed. So the only term here which decays only like 1 over R, a wave at infinity, will be when I differentiate this term, which means I have the minus sign twice, so I have minus to the 2, so I can do the computation with L indices, okay? If I have L indices here, after having proven I only need to differentiate this, I will get a minus 1 to the L when I differentiate this. Then I get the derivative di1R, di2R, L times over R, and I with L indices, 2 with L derivatives, okay? T minus R. Now, this is a unit vector, so this thing is minus L, IL with L indices, NL. Remember that NL means NI and NI2 and over R. Okay, this minus L cancels the minus L which is here, and at the end you can compute easily what is the 1 over R part of the waveform at infinity. And then you find that okay, so you have a wave at infinity. If you now you can project this wave, you can take the polarization of the wave. We said yesterday a wave at infinity, it is an object h mu nu which satisfy h mu nu, k nu, actually I have h bar, okay, k nu equals 0. So it is transverse to this thing and can be written in terms of a complex polarization, okay? And if I introduce a complex vector epsilon mu, which would be like e theta plus I e phi over square root of 2 or something like this, consider it's a spatial vector, but considered as a space-time vector, where theta phi, you know, is I have a some direction on the sphere, and I can take the derivative along theta and d phi to have a local orthonormal frame. So I introduce this object. And if I want the component of h mu nu along epsilon nu, this double copy thing, which is a good polarization, I can actually take the product of this by epsilon bar, because epsilon square mu is 0. But if I take epsilon mu, epsilon bar mu, this is 1 actually, it projects, so it is a way to project. So this is a way of getting in a seemingly covariant way what I want, which is the polarization, the component of the gravitational field in a complex form. And then at the end, you get that this thing is equal to yes, what is the best way to write it? Let me write explicitly the first terms, okay? Then you get 2g over r, it's the 1 over r component. There is a 1 over c4 if we want to keep track of this. And there is this polarization epsilon bar I epsilon bar j, because these are only components in space. And then what you find is a sum of terms. So actually, when you do the computation, this was a question of yesterday, the mass disappears because it is constant, so it goes like, it does not appear in the transverse wave at infinity, the spin is constant. The first moments that appear are the quadrupole, both of mass type and spin type. And then you find that the mass type quadrupole, this guy here, appears with 2 time derivatives because of this term, okay? And then you get Ij of u contracted with this simply. The next term would be the octupole with 3 indices, 3 time derivatives and 3 indices, and a coefficient 1/3 ijk of the retarded time u. And then this is contracted by an extra nk, because here I have only 2 indices. I want a tensor at infinity. And then the next term will have 2 n's. Let me not write. The j term, the opposite parity as a 4/3 of a coefficient, epsilon abi j with 3 indices ai and b, plus etc. So you get, this means 3 derivatives, okay? And yes, there are 3 derivatives here. It looks a lot. Anyway, yes, I think. No, sorry, there are 2 derivatives for this guy. Yes, like this guy. Now, this is here where you see the difference between orbital angular momentum and not, because in a sense, this object contains 1 unit vector nk. So if you wanted to ask how it rotates under the change of the theta phi on the angle, you would say maybe it has angular momentum L, orbital angular momentum 1. Okay, but still this is an object with 3 indices. So actually it is J equal 3 in the sense of quantum mechanics that we call L equal 3. Now, this was for linearized gravity, which is a rather simple exercise. So in linearized gravity, the final result is the following. You fully describe all the gravitational waves emitted by a source in terms of those 2 infinite sequences of multipoles. And the radiative, the ones that radiate energy at infinity, they start with the quadrupole of mass type, octupole of mass type, and then quadrupole of spin type, octupole of spin type. And these multipoles, they have several properties. First, they parameterize the solution. The solution is written in terms of these multipoles. These multipoles are expressed as integrals over the source. And the waveform at infinity is also expressed directly in terms of certain derivative of these multipoles. So in linearized gravity, the same multipoles do 3 things, okay? You know how to compute them in terms of the source. You express the field even if you are close to the system. And you express the field also at infinity. When you go to nonlinear general relativity, that is to say you solve these equations and not these equations, it gets more complicated. And this is where the multipolar post-Minkowskian formalism really is becoming useful. Let me just describe the final result, because I mean, it's the more complicated part. Part of the thing that one can see will do something useful is, you may know that in Landau-Lifshitz and also in Weinberg's book, people have noticed that if you take the nonlinear Einstein equations, the full equations, and if you work in harmonic coordinates, for instance, you can keep on the left-hand side D'Alembert operator acting on a linearized type object, the Gothic metric, and then all the nonlinear terms, you can put them on the right-hand side, and they complete the usual T mu nu of matter by a kind of so-called here Landau-Lifshitz stress energy tensor of matter on the right-hand side. And by the way, as I was telling Giancarlo, one of the reasons why Einstein took several years to build generativity is that already in 1912, he wanted to have a theory, actually in 1911, he wanted to have a theory of gravity where the source would be not only the energy density of matter, but the sum of the energy density of matter and of the gravitational field, okay? And he wanted this, okay? And as a requirement, and it was difficult to see which theory would do that exactly, okay? Actually, he realized in 1915 that general relativity does this, and he already computed the equivalent of the Landau-Lifshitz and proved the Bianchi identities and all that. Okay, so I'm saying this because part of the solution would be to say, and this was proven in our work with Luc Blanchet and further work by Luc Blanchet, that indeed you can use those formulas of linearized gravity, but you need to replace the T mu nu on the right-hand side by this combination, by, let's say, a tau mu nu. So you replace T mu nu by tau mu nu, which is the sum of G, the determinant for some reason of T mu nu, times the Landau-Lifshitz thing. So something conserved, which takes into account the local energy of the gravitational field. Okay, so, but this is only part of the answer, because when you solve Einstein's equations, if you have the source here, okay, so the multipolar post-Minkowski formalism does the following thing. It says it solved this problem by combining different things. It is difficult to solve Einstein's equations directly by solving the full equation. So, but what you can do is to separate the problem in two parts, which is to say we will solve the problem near the system by a local approximation, saying the system is moving slowly, and we use the post-Newtonian method to compute the field in this region. Okay, and then separately from this, you solve Einstein's equation outside of a tube where you have the vacuum Einstein's equations. And in this thing, you solve, for instance, if this is the Gothic metric means square root of G times G mu nu up, okay? It is eta mu nu, with this notation would be minus h bar mu nu of first order plus G square h bar mu nu second order. You can try to solve Einstein equation by successive powers of a small quantity. And then you find that h bar mu nu first order satisfy the vacuum equation in harmonic coordinates. And at second order, you find on the right-hand side that you have terms like h1, two derivative acting on h1, or products of h1 times h1, okay? And what you do is this thing you can solve exactly by a multiple expansion, because this is the general solution of Einstein's equation in vacuum, but just expanded in multiples. And then, so this, you can parameterize the solution of this in terms of two multiple moments of, let's call them, in the formalism, actually, you have to call them differently, but let's say you introduce two set of multiple moments, IL and JL, and it parameterizes H1. Then you replace this on the right-hand side, and now you solve this equation, which is difficult now, because now we have something nonlinear, and also each one of these multiples, it contains, 1 over r squared, like the dipole is 1 over r squared, the quadrupole is 1 over r cubed when you go to r equals 0, not at infinity, which means the right-hand side is very singular here. But this is normal because you want to solve here, not at r equals 0. It's not the good solution at r equals. But still, mathematically, you can solve this using analytic continuation in some complex parameter, which is a mathematical tool which allows to solve explicitly this thing, because one can compute. The interest is that you can compute explicitly this to second order. Okay. Now, what happens at second order? At second order, there are many things happens for this and this. For instance, among this term, there is one of the term which contains the m over r Coulomb field of the source, and then with two derivatives acting on the multiple moments, like IL of t minus r over r. Okay. And this is the combination, the product of the Coulomb field, which is like a 1 over r field of the source, and the wave emitted. This is a wave emitted by the system in the past, which scatters on the Coulomb field. And then you want to compute the retarded solution of this thing. So in terms of diagrams, as diagrams is just a way of representing that you solve Einstein's equation by perturbation theory, you have a gravitational wave which is emitted by the system and then which moves in the curved background, Schwarzschild background created by the source. And then this is called a tail effect, okay? So this term, already at this order, gives a tail term. Now, this term is more nonlinear in the sense it contains, for instance, IL over R times another IL with maybe a different indices over R. So products of gravitational waves, okay? This is linked to what I explained yesterday, the work of Yvonne Choquebrua, saying when you have nonlinear gravitational wave, the square of gravitational waves, even if they are small, can change the background. And in this formalism, it means, for instance, this is the energy of a gravitational wave, which goes like 1 over r square with the quadrupole moment, let's say, 3 derivative square at infinity. So you have quantities of this type that decay slowly at infinity, because 1 over r square is very slow, actually, when you solve it. So you need to solve this, you need to change gauges. At the end, the result is the following. You can introduce a set of multiple moments that you compute in terms of the source by this type of formulas, but in which you replace the T mu nu of the source by the sum of the T mu nu of the material source plus the nonlinear energy of the gravitational field locally in a PN expanded sense. This solves part of the problem, but you need to have more terms. And for instance, let me write, where is the thing? Yes, just to give you an idea, just maybe for the, yes. At the end, you find, for instance, that at infinity, yes, in nonlinear gravity, you get that the wave at infinity, so now it is epsilon bar mu, h mu nu, in nonlinear gravity, but it has an expansion of this type, where there is a term which is called uij, then there is a term which is called 1 over 3c uijk times nk plus 4/3, the same coefficient, let's say, epsilon abc, and then vja nb, okay? You can parameterize the wave at infinity also in something which has a quadrupolar structure. Under rotation, it rotates like a rotation 2L plus 1 with L equal 2, something which is octupolar. So these are called the radiative moments at infinity. These are the things which are observed by LIGO and Virgo. These are very far from the source. It parameterizes the 1 over r. Yeah, I forgot there is 1 over r here. The 1 over r part of the field at infinity, okay? And at the end, for instance, you get that uij in nonlinear gravity. First, you find that you should not express it in terms of t minus r, the usual flat space-time retarded time, but you need to shift it by 2g, the total mass of the system, g cube log of r, because the light cones are not flat at infinity. So you change the time, retarded time coordinate at infinity. And then in terms of this new good retarded time, nonlinear retarded time, you get something where the first term is is the same as this, okay? Except that on the right-hand side, you take the nonlinear gravity, nonlinear energy of the system. But then you have tail terms. For instance, you have a term which comes from this effect, which says that the radiative moment at infinity, at some moment, is not only a function of the state of the source at the retarded time t minus r, but contains an integral over the past, because what was happening in the past here, for instance, was scattered on the Coulomb 1/r field and then was rescattered towards infinity. So you get an integral over the infinite past, so 2gm over c cube times integral from 0 to plus infinity d tau, and the integrand is the fourth derivative of this quadrupole moment, ij of u minus tau, and then you have a logarithm of c tau over 2b0 plus 1112. Okay, and then you have nonlinear terms. Let me write the next further nonlinear terms. Like there is a term minus 2 over 7, integral from 0 to plus infinity of d tau, 3 derivative of this tensor, 3 derivative of the same tensor with slightly different indices. One index is contracted, the other is, and this is at u minus tau and u minus tau. This term is called the memory. So this term is called the tail, and this term is called the memory because it is linked to the emission of gravitational waves in the past, okay? And so we had this term with Luc in 1989, and then later Christodoulou rediscovered it in a rigorous way. And now it is taken into account in all treatments. And then you have many other terms, okay? So when you solve Einstein's nonlinear thing, you have many nonlinear effects that you need to compute. So the thing gets complicated, and Luc Blanchet has continued developing the multiple formalism and was able to compute the gravitational wave multiples, including all radiative and nonlinear corrections, to a very high order. And this is important for physics, okay? Now, this was the first part, now I think, and now I come to the effective one-body approach. Yes?
Question, do you have something, the Gauss law in general relativity?
Yes. In a sense, there are too many Gauss laws, yes. There are, because of Noether's type identities, which, by the way, were worked out by Einstein in 1913, 5 years before Noether, using variational principles. Because of the general relativity theory, okay, so there are two types of conservation laws where you can relate things to surface integrals linked to something, okay. There are, in a sense, too many of them. And the question is in which physical situation they give you a good information, okay? There is always conservation of total energy and total, let's say total energy and total linear momentum. If you ask even something which is simple in textbook, which is conservation of angular momentum in general relativity, this already becomes very subtle. And people fight about this. Okay, I will talk about this because some years ago, I did a computation using angular momentum radiation, and then some people said Damour uses the wrong definition of angular momentum, but gets the correct physical answer. So it shows that notion of conservation, I mean, there are many papers written about this, and there are conservation laws, but one has to see what is the physical meaning. The final point is maybe the following. When you have a full space-time generated by a source, like maybe a scattering problem, okay? It is not known today for sure. Whether the symmetry group, the real physical symmetry group of this situation is the Poincaré group or something, an extension, okay? And while we talk, in Capri, there is a school speaking of this, okay? So there are partial symmetry groups called BMS, but in my opinion, they are not global conserved quantities, okay? So, but still it is a research problem, you know? Because, why? Because of the slow 1 over r decay of the gravitational field, which means there are logarithm, the notion of infinity is delicate. In particular, I think that the usual, I mean, it's not that I think, and mathematicians like Christodoulou and Kleinerman think that the usual textbook definitions you see of asymptotically flat by Penrose and others is not applicable to the most general solution of Einstein's equations. Okay, this is a fact that it is not applicable. And therefore, you see there are many subtleties in gravity. 8 minutes, just the time to motivate EOB, which is good. So I will leave part of this, but I want to keep this. Let me erase this. So now we start considering the physical system we are mostly interested in, which is a binary system. So if I have a space-time diagram with T and space, a binary system is made of 2 world lines that go around like this. And you have a second one. Yes, this is where I should use the color. So 2 objects that go around each other. And the question is, what happens? Okay, what we know from the start is that these things emit gravitational waves. And now there is immediately the issue, which is problematic, okay, is you expect in usual physical theories that this system emits energy and angular momentum at infinity, that these waves carry away energy and angular momentum. Somebody has to pay for this, and then you expect that this is the system, the mechanical system, which is losing its energy and angular momentum. And this has been proven in some approximations, rigorously in perturbation theory, but you could explicitly check. And here we are going to assume that we will get the good definition of angular momentum so that it is true also, but this is still a problem, okay, for the future. But let's assume this, okay? Now, the traditional way of attacking this problem is to describe, so at any moment of time here, you have in space, you have 2 bodies that interact by gravity, okay? And then post-Newtonian theory, which means an approximation method where you start solving Einstein's equations at the lowest order, both in G over C square and in V square over C square. By the way, why G over C square? In Einstein's equation, you have G over C4. But T mu nu contains T00, the energy density, which is E equal mc square, which has a C square. So it means the right-hand side of Einstein's equation is really 1 over C square, G over C square. So this is the small parameter of the source. And then if you say the source goes slowly, then you can, if I have the time, I will say more about how you solve this. For instance, you can describe the conservative part of the interaction between 2 bodies by an Hamiltonian, which at lowest order would contain P1 square over 2 m1 for a body of mass 1 and a body of mass 2, 2m2, the kinetic terms, and then minus G m1 m2 over r, where r would be now r means r1, 2, the distance between the 2 bodies, 1 and 2. So this is the Newtonian Hamiltonian kinetic terms. Okay. If I go to the center of mass, then in the center of mass, I have P1 equal minus P2. And this is actually the P of the relative motion. And therefore, this Hamiltonian becomes P squared over 2 mu, where mu is Newton's effective mass, m1, m2 over m1 plus m2. We will keep this definition. And the second term becomes G m mu over r, where m is m1 plus m2, and therefore mu is m1, m2. Okay, so this is the Newtonian Hamiltonian. And then after this, you have correction in 1 over c squared, which means they are smaller than these by terms of the type gm over r c squared, or p squared over mu square, which is the velocity over c square and the product of these and things like that. So corrections of this type that I will write later explicitly are called first post-Newtonian approximation. Then you have terms 1 over c4, 2pn, 1 over c6, 3pn, 1 over c8, 4pn. Okay. When I started doing general relativity, the only thing which was known was this. Then actually with Nathalie Dervell, we were the first one to compute correctly this 2pn. Then with Jaranowski and Schaefer, we were the first one to compute the 3pn. And then with Jaranowski and Schaefer, we were the first one to compute also the 4pn. And then we will discuss that there is a method going beyond this at 5pn, which is the tutti frutti method. But actually, this is not known explicitly beyond this. Okay, it starts becoming quite delicate, and I will not enter all detail. But let's assume that we have some description of the Hamiltonian, which is Newton plus v squared over c squared correction, thing like that. Now, what do you want to write? And you first you go to the center of mass. Because you have a two-body system. So in principle, you want to know both the motion of R1 and R2, or the motion of the center of mass and of the relative motion. To a good approximation, the loss of linear momentum by gravitational waves is quite small at the 7th order in 1 over c. So there is some recoil that you need to take into account in some cases, but in first approximation, it is smaller than many other effects, so let's neglect recoil and consider that we look at the relative motion between the two bodies. Now, the equations would be Hamilton's equation. So Q dot is d Hamiltonian by dp, okay, as a function of x and p. And p dot is minus dh by dx, this Hamiltonian, okay. But this is the conservative dynamics. This is which conserved. Yes. So what you could explicitly check up to this order is that this Hamiltonian is actually has all the invariants of the Poincaré group. So it conserves energy, linear momentum, angular momentum, finally in the center of mass frame. But this is the conservative part. The system is losing energy and angular momentum. Therefore, you should add the radiation reaction force here that you can put here. And now, what is known about this radiation reaction force? This radiation reaction force, you tell me I will stop soon here. This radiation reaction force, which actually depends on the distance, at least like 1 over r squared. It starts at v5 over c5, a correction at 1 over c5, which means it is smaller than the Newtonian force by v5 over c5, or at least a gm here. Where did I write this? Yes, here. The next term is v7 over c7. These have been computed explicitly. Beyond this, you can assume what happens is after this, you start assuming that you compute how much you lose energy in angular momentum, and you say, I will put a radiation reaction force which takes into account the balance between the energy and angular momentum of the system and what is lost at infinity. And then this way you can compute terms at V8 over 9, V9 over C9, up to V10, okay, V10. Okay, you go as far as you can. And now you say, this gives a motion of two bodies with radiation reaction force. So what will happen is they will get closer, closer, closer. But you also need to compute how much you lose energy in angular momentum. And you need to know also what LIGO Virgo will observe. So you want not only to compute this, but you want to compute the wave Hi epsilon bar nu, h mu nu at infinity. You know, what is the wave in 1 over r with the multiple moment uij, vijk, what I was writing before. And where you are given by this formula computed in terms of the system. So it's a bootstrapped system where you need to solve the system, you compute how much you earn, then you put it back as a force on the right-hand side. And for instance, at lowest order, you find that Iij, the quadrupole moment of the system, is simply mu xi xj symmetric trace-free with v square over c square corrections and things like that that you put in this formula, you put. Okay, this way you can solve approximately what happens. And I will stop in 30 seconds. Yes, just to say that in 1964, Peters, I don't know, he's American, should be pronounced, realize that if you solve this problem at the lowest order by saying, I use the radiation reaction force corresponding to the quadrupole formula of Einstein, which is the leading order loss of energy in angular momentum, and I use the Newtonian description of the dynamics to start with, then what he found is that a binary system, which in general is moving on an elliptic orbit. If you are in Newtonian mechanics, the ellipse is fixed in space. If you add some relativistic thing, you know the ellipse will rotate a little bit. It's not very important at this stage. But then you lose energy in angular momentum. So the semi-major axis and the eccentricity will change secularly. And what Peters found is that the eccentricity goes faster to 0 than the semi-major axis, which is the energy, essentially decreases. So after an initial period, the system becomes essentially circularized. So the two bodies, they move on an approximately circular orbit, which is slowly now decreasing in size. And this fact, which is true, confirmed by higher order things, is very useful because it says that in first approximation, and in reality for most sources you will observe from a binary system, as they evolve from 100 million of years, you know, they will be circular most of the time, especially when you catch them at the end. And then it means you can compute all the dynamics for bodies moving on circular orbits, which for many reasons is simpler than if there is elliptic and precession and things like that. And just to finish, in this PN approach, if you compute now, if you say, I take the circular limit, and then what you get is an equation, and there are textbooks where people say, this is a good approximation, but this is where EOB will say, no, you need to go beyond this. You write essentially the equation, which is that the time derivative of the mechanical energy of the system, which is the value of the Hamiltonian along a circular orbit, and you can express this in terms, let's say, of the velocity, circular velocity of the system, should be equal to minus the flux of energy in the form of gravitational waves at infinity that you compute along a circular orbit, and there is only one parameter, the velocity or the radius of this circular orbit. This equation tells you that dE by dV times dV by dt is equal to minus the flux of energy as a function of V, and then this gives you a differential system for dv. Okay, it gives a differential equation that you can solve, knowing that you know E as being a sum of terms like that, 1 over r, 1 over r squared, etc. And you know also this as being the quadruple formula plus the next term and things like that. Okay. For instance, you find that if you do this, and if you use the multipolar post-Minkowskian formalism, you can compute this flux of energy to high accuracy. And you find that it is equal to 32 over 5 times GC5 times nu square V to the 10, where nu is nu over m, so the effective mass divided by the total mass. So this is the product of the two masses divided by the square of the sum of the two masses. This is a parameter which is equal to 0 when one mass is very small and 1/4 when this is equal mass. And everything is a function of nu, okay? And at lowest approximation, this is Einstein's quadruple formula from 1918, 32 over 5. And this thing has been computed to high accuracy, v squared over c squared, v cubed over c cubed, etc. And for instance, if you look at the term which is v6 over c6, you find that its coefficient is 123 minus 16 a log 2v over c. There are logarithms. The logarithms are linked to the tail effects which contain these integrals over the past. Okay, so you have tail corrections. But numerically, you find that the coefficient is of the order 100. And now, if you push the calculation to the end, the two bodies will get closer, 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 closer. And when you estimate at which moment two black holes will merge, this will be then when V over C is of the order of 1/2. You find for some reasons, okay. But when V over C is 1/2, you find that this term numerically is of the order of 2, is larger than 1, which means that you have an expansion which is not, 1 plus a small number plus an even smaller number. You have an expansion which is 1 plus 1 minus 1 plus 1 minus 1 plus 2 minus 3, which means that if you use post-Newtonian approximation, you can describe what happens when the two bodies are far away from each other. But the most interesting moment, which was observed by LIGO-Virgo, which is the last orbits, you cannot describe. And this is the motivation of the effective one body, which is to not use this formalism and use something else that has a chance of being valid up to the moment of merger, and actually was shown to be valid up to the last moment. So after the break.
Thank you. Time for a few questions.
Can you say something more about the logarithmic correction that appear in the tail? What is the origin of this logarithmic correction?
So actually, this logarithm is obtained after integrating by parts. One cannot say, it is true, there is a logarithm, and then the 1112 is really there. But here you have 4 derivatives. So if you want to say this is a correction to this object with 2 derivatives, and if you want a kernel which acts on this thing with 2 derivatives, you need to integrate by parts, and then the log becomes 1 over tau square, etc. Okay? So it is a power law, independently of everything. These tail effects, they contain power laws. Okay? But precisely which power law you want to see, it's a little bit up to you. The result must be equal to this, okay? Okay, it's not a completely satisfactory answer, but it's not always a log. In some cases, you will see something else than a log.
More questions? Okay.
But what is important in the log, yes, I should have said this, is when there is a log, because it is a log with a time difference, it means you need to put a scale, yes. So, and you say, so which scale do you put? But now, this scale, if I change the scale, what happens is that it's just a time shift. So there is an ambiguity of a scale, but this ambiguity has no physical impact because it corresponds as what is. There is another logarithm, which is this logarithm, which also, because it is a log of r, I need to put a scale here. And what happens is the scale I put here cancels the scale which is here. So in that sense, there is really a logarithm in the tail. Okay.
Thank you. Let's reconvene in half an hour from now, okay?
No, più che altro, vabbè, magari riesci pure a capire il background e scrivi, però è come se tipo il tuo cervello però non è che capisce il significato, cioè capisci la forma, la parola. Allora, perché sono però sì, però questo cioè, può fare dopo.
Yes, yes, part of the, yes, definitely. Yes, the radiation reaction form. Okay, here I was looking on the relative motion. The full frame of the radiation reaction takes record. And you must take it into account also. Because you have to make this expansion to yes, and then record is important. But still, in spite of the complication of the thing, first, pedagogically, you don't want to say all complication at once, and even practically speaking, the recall is something you can add as an extra thing linearly in itself without taking non-linearly. So in that sense, you can add it at the end. While the radiation reaction here, now you need the square of the radiation direction, which is more subtle. So you can see there are levels of subtlety. Thank you for your time. Yes, you got it. But it is, they are probably better flexibility, right?
Giusto come se ne dica, se no dica tutto, io faccio uscire il tempo.
Comunque pure il regista non c'era la lavagna. Ma sta un problema, è stato molto lontano.
Okay. Soon, Professor Thibault, Damour will start the second part of the lecture.
One needs to. No, it works. Okay. Yes.
Okay.
So now we enter, I will explain what were the various ingredients of the effective one-body approach to the dynamics of binary systems. The basic motivation was the following. We have sketched here that if you use usual perturbation theory, expansions in V over C and in the gravitational potential Gm over RC square, this is very good if the two bodies are far apart, but it loses its validity in the last 5 orbits or so, and this is bad because this is really where you want to describe the signal very accurately. And the basic idea, there are the key word in the effective one-body approach is resummation methods, okay, or resummation, which is to start from a knowledge in perturbation theory computed way. For instance, here I have written explicitly what is the Hamiltonian of two bodies in the center of mass frame at not only at the Newtonian approximation, which is this first term, but at the next order of approximation by using scale variables. Here in the full form, you know, there would be 1 over 2 mu, there would be gmu. You can rescale distances by gm and divide by mu, so that's why there is a hat here, so that the Newtonian Hamiltonian is just p squared over 2 minus 1 over r, simpler. And then the Einstein-Infeld-Hoffmann, so the next correction, which has v squared over c squared, was first computed fully by Einstein-Infeld-Hoffmann in 1938, although actually Lorentz Strauss computed it in 1917. And already you see it's not trivial, okay? If you added just an extra term 1 over r squared to the potential minus 1 over r, you would see immediately it's a simple mechanical problem. Why you have terms in the 4th order in piece P in the momenta, you have terms coupling 2nd order in momenta with 1 over r and terms in 1 over r squared, okay? And when you go beyond the 1pn approximation, this thing becomes very complicated. Okay, if I was using slides, I could show you pages of explicit values at 2pn, 3pn, 4pn. It starts having, you know, 100 coefficients, which means it is also not very good to use. It's complicated, and you don't know immediately what to do. So the basic EOB is resumming two things. Here, the basic physics we have here is to say we want to decompose the dynamics of two bodies in a conservative part described by some type of Hamiltonian and a radiation reaction part. And the radiation reaction part is linked to the emission of gravitational wave at infinity, okay, Hij at infinity. So EOB has introduced new ways of resumming separately the conservative dynamics, let's say the Hamiltonian, and resumming the waveform, so that later with the resum waveform you can compute a better approximation of the radiation reaction that you put in the conservative dynamics. Now, concerning the first part, which is a resummation of the Hamiltonian, and then we will talk about the resummation of the waveform in the second part. The basic idea is the following. When you compute this, it means that in space-time you have two world lines, and then you compute the interaction via linearized gravity. This just means, you know, 1 over r potential in a relativistic sense. But you must add, here you have terms, you know, which are 1 over r squared, and they come from the fact that you have nonlinear effects, that the gravitational field created by the second body is itself creating nonlinear energy, gravitational energy in the middle, and this creates a force on the second body. This is what means this diagram, and it is connected to this type of things. And then when you go at higher order, you have more and more complicated things, and this gives a perturbation theory. So this is a two-body problem with mass m1 and m2, okay, interacting by the real gravity. Now, the basic idea is to say, can we replace this problem in the same way that Newton did? Newton noticed that the two-body problem, this problem, is equivalent to one body of mass, this effective mass, moving in this potential, in the real two-body potential. Okay. Which is already non-trivial because when you have two bodies, they move both, but the relative motion simplifies the thing. Is there an analog in nonlinear general relativity? So does it exist? Initially, the idea was, does it exist some effective metric, G mu nu effective, in a fictitious spacetime, which has nothing to do with the real metric created by the two-body system, such that if I take a particle mu of mass mu, which follows a geodesic in this spacetime, which means that its action is minus integral of mu, the DSF, you know, square root of minus G mu nu effective dx mu dx nu. So this is the action of a test particle in some external effective metric. Does it exist? An effective metric such that the geodesic motion of a particle of mass mu is equivalent to this complicated thing, okay? And surprisingly, the answer is essentially yes, with some correction, and this is why it is useful, because it simplifies a lot the two-body problem by replacing it by an effective one body. Now, what is, okay, this is the action for a geodesic. The corresponding Hamilton-Jacobi equation or mass shell condition is saying that the inverse of the effective metric in its spacetime X times P alpha, P beta plus mu square must be equal to 0, okay? This is the mass shell condition. In Minkowski spacetime, we know that we have E square equal, you know, P square plus M square, or E square minus P square equal M square, okay? And this is this equation. If you are in a curved spacetime, the momentum of the particle of mass mu should satisfy this mass shell condition of this type. So you look for an effective metric such that this is equivalent to this complicated thing. And now, a priori, it's not evident to say, okay, it's nice to say this, but how are you going to compute something, okay? What do you do after saying this? And this is something I had learned from Wheeler when I was in Princeton a long time ago, that Wheeler was saying regularly that quantum mechanics help you to understand better classical mechanics. And if you think about what is the essence of this dynamics for two bodies and the essence of the dynamics for one body in an external thing, it clarifies the thing. Because indeed, if I have a two-body system, like if it were electromagnetism, I would say, quantum mechanically, I have energy states, okay? And energy states, they are characterized by the quantized angular momentum, okay? L, which is an integer times h bar. And then I have states which are formally, you know, zero angular momentum, S states, P states. So it's L equal 0 h bar, 1 h bar, 2 h bar, okay? And for each value of the quantized angular momentum, I will have some energy states, okay? Which for a Coulomb problem would be something like this. Okay, those quantum states. Now, if I have also here a particle of mass, so this is the real energy, and I have this. Now, if I have this particle of mass mu in some external field, but which will contain a 1/r attractive thing, I will have also states of this type, but with here is the real angular momentum. And here I will have the angular momentum of this particle in its space-time, okay? And then I will have the conserved energy of this problem, the effective energy. And then I will have also states, quantum states. Now, just drawing this picture allows to solve the problem, essentially, because evidently, if you want to say this is equivalent to this problem, you want to say that there should be a state here corresponding to a state here, a state here, to a state here. They should correspond state by state, okay? Now, in the semi-classical limit, the Bohr-Sommerfeld quantization condition is telling us that we have integers, which after you correct them by 1/2, okay, satisfy this condition 1/2 pi integral of pi dqi. That is to say, for systems which are integrable with multiple integrals, you have the action variables, which are the integrals of p dq over the separate degrees of freedom. For instance, here you will have, this is not sum over I, okay? This is for a fixed ni. You will have the radial action. You will have, if I take this coordinate to be phi, this thing becomes p phi. It's p phi d phi divided by 2 pi over one circle, so 2 pi cancels, and this means I phi. And we know that usually you have a good real, how is it called? The principal quantum number is L plus NR plus 1, okay? Where you make the sum, because the solution of the Coulomb problem is that the energy states are given by minus 1/2, 1 over L plus NR plus 1 square. Okay, this is the Coulomb solution of the, you open a textbook if you forgot about this, and then you get this. And then when you have relativistic corrections, you have those states as quantum states are function of integers, okay, on both sides. And therefore, it is clear that if you want a correspondence between this problem and this problem, you should say, each integer here should correspond to an integer here. But in the Bohr-Sommerfeld quantization, what is integers are the action variables, okay, integrated over each degree of freedom. And therefore, this thing tells you what you want is to say that the real radial action is equal to, you make a correspondence such that it is equal to the one of this problem, and I phi, which is the p phi of the real problem, is equal to the conserved p phi here, which is the p phi, this capital P phi, different from the p real. Here it's the p real, so it's the real angular momentum, and you want to say that the conserved angular momentum of this thing is equal to the real angular momentum, okay? And then you want to say that when you take the limit classical limit, where those states become, h bar goes to 0, the energy as a function of these integers become what is called in France the Delaunay Hamiltonian, which is the energy, the real energy, as a function of the real radial variables, okay, action variables, II and I phi. And then you want to say that there should be a correspondence between this and the effective energy as a function of II and I phi, where I have identified the variables here and here and here and here. But what I don't know is this effective energy cannot be the full real energy, because the full real energy is the two-body thing which contains M1 plus M2 also, while here it is like only some energy linked to the mass mu, it lacks something. So I should allow for the existence of a function which change this energy, the effective energy. So what is the effective energy here? When you have an Hamiltonian of this type, if this thing is independent of time, that we're going to assume, you have P0 is conserved, okay? And P0 is minus the effective energy, because the index is down and I'm using the signature, okay? So here I have a conserved energy, and I don't know a priori what is the link between this conserved energy and the real two-body system. So at the end, you want to say I look for an effective metric such that an equation of this type is valid, okay, which is a mathematically well-defined problem, especially because
You mean that the problem is periodic, so somehow there is no loss of any.
yes, I'm talking here about the conservative dynamics.
Yes.
So indeed, here we are saying we forget about radiation reaction. We take the part of the dynamics which is conservative, and then we identify it to simpler dynamics. Okay, indeed. Thank you for the question. But now there is something more, is that although this is a two-body problem here, this two-body problem is spherically symmetric in the sense that it has no preferred direction in space, okay? And therefore, it should be equivalent to an effective metric which is also spherically symmetric. But now, an effective metric which is spherically symmetric, it is easy to write down its general form. So let me write it. It would be given by an effective metric, G effective nu dx mu dx nu, which is of the type minus a certain function over c square dt square, the time, plus a function over dr square, plus r square times d theta square plus sine square theta d phi square, okay? If I have a spherically symmetric metric, I can always go to coordinate system where the angular part is r squared, it defines r, okay? And so I have two functions a and b. And now, but here I have two functions a and b and an unknown function f. So it's difficult to solve the problem. But you solve it by saying, but I want actually this identification to be true in perturbation theory, which means at each order in expansion, okay? And here we will discuss each order in the Pn expansion, which means first we will look at the metric which gives the Newtonian thing, okay? And then the 1Pn, and then the 2Pn, and then we will see if at each order we can find something. And also it means that I want this function, a of r and b of r, to have an expansion around flat space also. Like for instance, I want this function to be 1 when, let me write the thing, okay? 1 plus a1, maybe a coefficient, times gm over c square, let me write it here. a1 of nu gm over c square r, plus a2 of nu gm over c square r square, expansion in powers of g over c square, and b is also of the same type with coefficient gm over c square r plus b2, okay, gm over c square r square plus etc. Now, the 1Pn, the Newtonian approximation actually consists in using only this term, okay? In Einstein's theory, the modification of the 0,0 component, this is the component of the time component, okay? In lowest approximation, it's 1 minus 2m over r. So you expect, actually, if you want, and now I need also to parameterize the arbitrary function because I don't know yet what is the relation between these energy levels here and the real energy levels there. So this also, I introduce a parameterization, which is that the effective energy in the lowest approximation, it should give mu c squared, the mc square of the particle. So this should be 1, okay? So in lowest approximation, I have 1. And then after this, I have corrections, which is irreal if I subtract mc square of the two body systems. And to make it dimensionless, I divide by mu c square, okay? Actually, you can argue that this should be already true at the Newtonian approximation with a coefficient 1. And then after this, you can look for coefficients such that this thing, E real minus m over mu with c square plus alpha 2. Okay. Now, the problem is simpler because you parameterize by coefficients of perturbation theory. And you say, do there exist coefficient A1, A2, B1, B2, alpha 1, alpha 2, such that this equation is true. And now it is fully algorithmic because this function you can compute. How do you compute it? You need to solve the real problem, two-body problem, by going to action variables. You compute perturbation theory. You compute all the, and we had done it actually with Schaefer at 2pn and then 3pn before. So this function was known before, okay? Now you can do the same type of calculation for this effective thing, which is just a different geometry, but you do the same integrals. And then at the end, you have a set of equations, and you ask, is this set of equations, does it admit a solution or not? And the answer is with some qualification, yes. And I will just describe the results. Okay. At the Newtonian approximation, which is very simple, it is one line, you find that it is enough to take this coefficient A1 to be -2 and to neglect all the rest. And this is the Schwarzschild metric. Okay, it's the linear. Okay, it's actually what Einstein wrote in 1915, that G00 modulo sign is 1 minus 2 GM over C square R, okay, on both sides, okay? And then everything works. So it is trivial in a sense. At the 1pn approximation, actually it's a non-trivial calculation, okay? Even the gifted students here cannot do the calculation in 1 minute, okay? It takes some setting of the integrals there and there, thing like that. And what you find is actually you have 3 unknowns, because at the 1pn approximation, now you include this coefficient, and this coefficient, alpha 1. So you have, let me put some red. So you have 3 unknowns, which is this alpha 1, this A2 now, and this B1. And if you look at the number of equations, so you have 3 unknowns, you finally have only 2 equations, okay? So actually you have more solutions than what you want, but it seemed in our initial paper with Alessandra Bonanno, where we did that, we said it seems very natural to assume that at the linearized level, this coefficient is also the same coefficient that would be for a Schwarzschild metric, okay? Because it looked something that should be true also. Yes, let me mention also, again, the coefficient nu here, this parameter nu is mu divided by m. It's a dimensionless parameter because I forgot to say that one element of the effective one-body is to say we are interested in 2 masses which are comparable a priori, maybe equal or not equal. But I can also take the limit where one mass is very small compared to the other one. In this limit, I know the answer. This is the probe limit, and therefore in this limit, I know the answer to the question is yes. I am just taking a probe particle going around a black hole, Schwarzschild black hole, if it is not spinning. So in that case, we know that when nu goes to 0, all those coefficients should reduce to the Schwarzschild metric. Okay. Now, if you assume simply for simplicity that you fix B1, the coefficient here, so we said this coefficient here is -2 from the Newtonian approximation. If we say B1 is +2, which is the value for the Schwarzschild. Let me remind you that the Schwarzschild metric is -1 minus 2m over r dt square plus dr square over 1 minus 2m over r, okay, plus r square d theta square, etc. So when I expand this, I get +2 here, okay, the inverse of the other one. When you do that, you find a unique solution, and which is very simple, because you see, here you have all those complicated coefficients. They depend on nu, you have 8, you have 3, you have PR square, you have 1 over 2R square. So the equations involve some complications, but at the end, you find that the solution is A2 equals 0, so that you don't need this term. and that alpha 1 is nu over 2. Okay? And this fact means what? This fact means that already this Einstein-Infeld-Hoffmann 1pn dynamics, which is non-trivial, if you want to compute it explicitly, is equivalent to an effective metric, which is what? Which is minus 1 minus, let's say, 2m over r dt squared plus dr squared over, because this is the opposite, over 2m over r plus r squared d theta squared plus. So I put a test particle in this spacetime, which is Schwarzschild. So a test particle of mass mu in Schwarzschild is equivalent to the already non-trivial, Einstein-Infeld-Hoffmann 1pn. So at this stage, we felt, maybe indeed it introduces simplifications, this fact. But the price for this to be equivalent to this equation written in terms of this, you need a transformation between the real energy and the effective energy, which, when you write it explicitly, is that the effective energy divided by mu c squared is equal to the real energy square minus m1 square c4 minus m2 square c4 divided by 2 m1 m2. At the end, you find that the effective energy, the conserved energy of this, is essentially Mandelstam invariant, the square of the total energy of the system minus this shift, okay? Which also looks simple because it had appeared before. It looks like a simple answer. And now you continue to the 2pn, and at the 2pn level, you find again that alpha 2 is 0, so you find again the same thing. At 3pn level, you find that the next term is 0. At 4pn level, so this way of solving the thing said, yes, this transformation between the real energy of the system and the effective energy is valid seemingly to all orders that we could compute, which was a sign that there was something simple. And the only thing which is slightly complicated is that the effective metric becomes slightly more complicated, but still much simpler than what you had initially. Because, yes, let me write here. Okay. Yes, for instance, at 3pn, what you find, and I will also describe 2pn, you find this function A, which is the coefficient of G00 of the effective metric, in terms of the variable U, which is no longer the retarded time, but which means Gm over C square R. So it is 1 over R. So at lowest order, this is 1 minus 2U, which means 1 minus 2 Gm over R. So this is Schwarzschild. At the next order, I said, and this was a surprise, that the next coefficient U square is 0. Actually, you don't need to put U square. At the next order, which is already 2pn level, so this is 1pn level, you have a coefficient of U cubed, which is just 2 nu. Why, here I cannot write the 2pn thing, but the 2pn thing is much more complicated than this, and it is summarized in a coefficient 2, simply. So, by the way, and I remember when with Alessandra we did this computation, this coefficient is obtained by a combination of terms that cancel. You get 0 by, 2 minus 2. And this term also, there was a nu square and a nu cube, which canceled, okay? So one felt there was some simplicity in this game. And then if I take the product AB, because in Schwarzschild, A times B, okay, is equal to 1. So you say, let's compute instead of B, the product A times B. You find that this is 1 minus 6 nu U square, okay, which occurs at 2pn also. And then at the next order, so at 3pn, here you have a coefficient of U4, which is, again, after a lot of cancellation, simple because it is proportional to nu with a non-trivial coefficient, which is 94/3 minus 41 pi square. There is a pi square coming in over 32. And here you have a coefficient D3 linear in U, which is n quadratic in U cube. So this is the 3pn level. And at the 3pn level, you also need, in the mass shell condition, the mass shell condition is G alpha beta, P alpha beta, P beta, plus mu square. You need to put an extra term, okay? These terms are quadratic in momenta. And then we found that you need to put terms which are quartic in momenta. Okay, but it looked like a small price to say. It's not really a geodesic. But this is okay. In effective field theory, you expect to have terms which are higher in momenta. And the coefficient is simple. 4 minus 3 nu times nu times u square times PR over mu to the fourth, okay? And then it continues at higher order. So at the 3pn level, for instance, what was remarkable is the 3pn Hamiltonian is really complicated, but it is all the information is contained in this coefficient, and this coefficient. Okay, so it looked like a good starting point, but there was one caveat, which is, okay, the potential A is in Schwarzschild, you know, this is 1 minus 2m over r. This is the main gravitational potential, okay? And if you consider, actually, if you consider the states of the particle mu going around, there is an effective potential. A is an effective, if you want the effective potential, which contains centrifugal effects, and in Newtonian thing, the attractive part is minus 1 over r, and the centrifugal term is L square over r square. And the sum of the two is the effective potential for orbits with angular momentum. If you do that in the relativistic setting, you find that the analog of this thing is 1 A of r times 1 plus L square over r square, okay? And now let us first consider, so this potential A of r plays the role of the main attractive part, and then when we need, we will say there is the extra term coming from the L square over r square. But first, let me not consider L square over r square, and just plot A over r. A over r is always of the form 1 minus, it's written here, okay. It's 1 minus 2m over r plus 0 m square over r square plus 2 nu r cubed. So let us plot this. As a function of r, at infinity, this goes to 1. And then at the lowest order, you get 1 minus 2m over r, okay? At this order and also at this order, okay? So this is saying that I have an attractive potential. It looks okay. At the next order, 2pn, I have this correction, which is 2 nu u cube. Nu, the maximum value of nu when the masses are equal is 1/4. It is m1, m2 divided by m1 plus m2 square, okay? So even if you take nu equal 1/4, you find that this extra term gives a potential which is like this. It is slightly less attractive. So here what you find is when you have two black holes, the nonlinear field energy due to nonlinear Einstein gravity makes the attraction of the two things less attractive than if they were in the test, in the probe limit, okay? And it continues. At 3pn, this term is also positive. Positive means you will go up from this. But now this coefficient is large. This coefficient here is numerically equal to 18.68. And then if you compute this effective potential, including this gem over alpha, you find that it is like this. And then it is so less attractive that it becomes repulsive, okay? So at this stage, then this was done with Jaranowski and Schaefer, we said, it's okay. We know resummation. What we want is something which is of the type 1 minus u, which has a 0 somewhere, to be attractive, and therefore we replace this thing by a pade. We take the pade, which if I stop at this stage is a pade 1,3, okay? A pade 1,3 means I replace 1 plus u squared plus u cubed plus u4 by 1 plus u at the top, and below 1 plus u plus u. So I put the 1 above and the 3 below, so that it is close to 1 minus 2u. Okay. And when you do pade, you replace this thing, let me take the red, by something which is like this, which is indeed less attractive than the thing before, but still attractive enough to be continuously connected to the probe limit, because you want, the effective one body is also saying, I want to have a deformation of the test mass limit, which is continuous, that something does not happen for mass ratio equal, something which is completely different from small mass ratio. Yes, good. But for instance, this point here is the point where this function is 0. If I am really in the Schwarzschild limit, the probe limit, this is the horizon, okay? And the fact that there is an horizon means a black hole is very, very attractive, even before the horizon, like at 3M, okay? So here, what we are saying is that when I have two black holes, there is an attractive force, but less attractive. But with this resummation, it's still quite attractive, but less attractive in the sense that this thing here, it is 2 GM. The value of R, which makes this 0, is this. Why? For this thing, after pade, it is 1.2 something, which I put somewhere, 1.244 GM. So you see that in a sense, there is an effective horizon, which is closer, okay? But now, let us take not only this potential A, but what I was saying, which is the full effective potential, which is if I want to study all the orbits, elliptic orbits, circular orbits, I need an effective potential, which is just this, which, by the way, it shows how UB simplifies technically things, that if you say, I have the 3pn expanded Hamiltonian, I want to compute elliptic orbits, it will take you, even with Mathematica, some time to set up the problem, elliptic orbits. Why here you say, I can write the answer immediately. I multiply this function by 1 plus L square over R square. And then what? What happens is that this effective potential, now that this function has a 0 somewhere, let's say at 3pn, it means this function will vanish here. If L is very large, which means I put a lot of angular momentum, I have a centrifugal L square over R square. Let me remind you that in Newtonian approximation, this thing is saying the Hamiltonian is P square over 2 minus 1 over R. And then I can say this is P R square, the radial part, plus the centrifugal part, L square over 2 R square minus 1 over R. So the effective potential for radial motion is minus 1 over R, this thing, plus L square over 2R square. So something which is minus 1 over R and plus L square over R square, and they combine to make orbits going around an attractive mass. So what happens here is the same thing. If L is large enough, the fact that it vanishes here means I have something like this, and therefore this goes to 1 at infinity. And then we see that if L is large enough, there will be circular orbits if I put the thing here. If I put more energy, I will have elliptic orbits going like this, and I can qualitatively see what happens. But then, because this thing vanishes here, if L squared diminishes, what happens is that this thing will start being like this. And then at some point, this mountain, the hill, which is a centrifugal barrier, will disappear. And this is well known for Schwarzschild. That is, around Schwarzschild, you have circular orbits if they are far enough and have large enough angular momentum. But when they get closer than 6 GM, 3 times the horizon, you have a point like this, okay, an inflection point, and this is called the last stable orbit or the innermost stable circular orbit, which is saying that when a test particle goes around a black hole, it can, if it loses energy, it will get closer and closer on circular orbits. And when it arrives at 6 GM, it has no circular orbits, stable circular orbits anymore, and then it falls in the horizon. This is what happens here. So you have a continuity. So the idea here is we have a deformation of the probe limit where we think, okay, so you see conceptually what we were saying when we constructed that is because now after that we said now we think we can use this formalism to describe orbits up to the last stable orbit. Why before people said no, perturbation theory is too bad, you cannot go to the last stable orbit. But even better, because then, okay, then we added radiation reaction. So at this stage, we said, let's take the same equation as before, but now we have resummed the dynamics. So we have a problem with a real Hamiltonian. H, the real Hamiltonian is obtained by solving this equation. So the real Hamiltonian is obtained by saying, here I put the Hamiltonian, the real energy, and here I put the effective Hamiltonian, defined by this formula, and I solve this in terms of this, which means that the real Hamiltonian, actually divided by m, is equal to square root of 1 plus 2 nu, the effective Hamiltonian divided by mu, minus 1. At the end, if you solve, okay, it's a second order equation, so it's easy, you get that the real Hamiltonian is the square root of the effective Hamiltonian, which is itself a square root. So you have a square root of a square root, which resums things already. It's at high energy, it's good. But now, this is the conservative part. Now we need to put a radiation reaction part, okay? And at the beginning, we did try to resum the radiation reaction part, saying, okay, this radiation reaction part, I have sketched before that it was given by a PN expansion. When you look at the PN expansion, first you can understand why it is not well convergent, because it has a pole in the complex plane. So you say, okay, I factorize this pole. And after that, you still have an expansion. And then you say, I pad it, because when you have an expansion, you don't know any special information. You replace it by a rational function, and it should be, in general, better, okay? So this is what we did initially. And then I will describe maybe next time that with Alessandro Nagar and Bala Ayer, then we invented, how much time do I have here? 5 minutes? 2 minutes, okay. So let me just give the idea. So with some versions of radiation reaction, and this resum Hamiltonian, which contains this sequence of orbits somewhere, you can qualitatively see what happens, because what happens is initially the two bodies are at certain distance, and they go on an essentially circular orbit, according to Peters. But now, this is the angular momentum. But the angular momentum, you lose the angular momentum. So as you go, this thing goes down, goes down, goes down, which means the two bodies will go like this. And at some stage, they will reach here their last stable orbit. And then, because you put radiation reaction, and then something will happen. And before our work, people call this the plunge, as if when you reach the last stable orbit, suddenly you plunge like this. Actually, what we found is you don't plunge at least like this, because this is clear from this thing. When you are here, the potential when the L is slightly smaller is like this. So it means you are on a very flat potential. You still have a radiation reaction which pushes you down, but slowly, which means that after you cross the last stable orbit, actually you slowly, you don't plunge like this, you go towards the two bodies get closer and closer, and then you compute the gravitational wave emitted by this thing. You say, okay, let's compute the gravitational wave, and in particular, you can compute the orbital frequency, omega, as a function of time, which gives essentially half the gravitational wave frequency. Because for circular orbit, the fact that the gravitational wave is emitted in the L equal 2 mode means the frequency of the gravitational waves is twice the orbital frequency for circular orbit. So this is like half the gravitational wave frequency. And what you find is for a long time, this frequency is slowly evolving because you get, they get faster, okay? You lose energy and angular momentum. And then you reach the last stable orbit. And then we said, okay, let's continue. We have nothing to lose. And then what happens is if you compute from EUB, just solving this equation, just ODEs, okay? You find that this frequency has a maximum and then goes down. But what is this maximum? This maximum, when you look at it, essentially corresponds to what is in Schwarzschild the light ring. Remember that in Schwarzschild, you have the last stable orbit at 6 GM, and then when two bodies get closer, there exist photon orbits, which would be represented by things with very large L at 3 GM, okay? Where the photon at the velocity of light can go in an unstable orbit around a black hole, okay? The same thing happens in EUB. And then I had learned when I arrived as a postdoc in Princeton from Remo Ruffini that in Princeton, Ruffini, Thiomno, and Davis, Ruffini, Thiomno, had computed what happens when a particle falls in a black hole. And then what they had found is when the particle falls through the light ring, actually it starts exciting quasi-normal modes. And this is the transition between a particle which is essentially in flat space-time and a particle which now excites the vibration of a black hole. And then we said, okay, so it seems natural to assume that when you reach the light ring as defined in EUB, because it's not the usual 3 GM, it is defined by the formalism with the resummation and the pade, we say, and we looked also at how the thing looked, and then when you looked at the two black holes, they touched, essentially. And then we said, so when we are here, we have two black holes going around each other, far away from each other, okay? Then at this stage, they are already close. They go around. At this stage, the two black holes, we were saying, let's assume that they are so close and the equivalent space-time is so strong that it prevents gravitational wave going to infinity like in flat space. We are no longer a nice wave going to infinity, that we are going to merge the two black holes and that they are going to vibrate, because when you have they will make one black hole that vibrate. And then we said at this stage, the gravitational wave here is a sine wave. And at this stage, we said we replace the gravitational wave computed from the orbital motion by a sum of quasi-normal modes. That is to say, it was a rough approximation saying in the effective one body, either the two bodies are like 2-point masses, but we push the approximation up to the moment where the two black holes touch. And then we say, it's an approximation, the two black holes merge and become an excited black hole, which is known since the work of Vishveshvara and Bill Press, that it emits quasi-normal modes. And then we said, let's compute the full gravitational wave emitted by this procedure, where everything is predicted analytically from EOB, yes, because the final thing is to say, we start from perturbation theory, we resum the dynamics, we resum the radiation reaction force, then we predict both a motion of two bodies, radiation reacted, and the gravitational wave emitted, purely from perturbation theory, but which, surprisingly, saying we describe the merger of two black holes, which our colleagues in America used to say, no, it is impossible. Nobody can predict from perturbation theory the merger of two black holes. We need numerical relativity. But when we did that with Alessandra Buonanno in 99 and 2000, there existed no numerical relativity. So we said, let's bet that this thing will predict a good approximation of the full gravitational wave emitted by the in-spiral and the merger and the ring down of two black holes. And indeed, at the end, our prediction was quite close to the full answer, which was obtained only 5 years later by numerical relativity. And so this was a prediction about the overall shape of the signal. It even predicted how much angular momentum the final black hole should have, how much energy it should emit. 5 years later, when numerical relativity gave data, one could compare the numerical relativity waveform to the purely analytical EOB, and they coincided to 90%. And so, which still meant there was 10% error that we needed to correct. But then you use the idea is having numerical relativity, which describe more accurately what happens here. You use this information, and let me just say one conceptual point here. Like for instance, analytically, you last point. Yes. The next coefficient here in U5, which is 4pn, we computed actually with Jaranowski and Schaefer. And the next to next, which would be u to the 6, the coefficient here is known, which is 5pn. You know only the logarithmic contribution, because logarithms are easier to compute, but you don't know what is the finite part A6 here. Here it's the coefficient called A4, A5, A6. So what you do, just to give an example, is you don't know this A6. It's not computed analytically. You say, I don't care. I put it as an unknown coefficient. I Padé resum this with a Padé 1.5 now. I have a prediction for an A function, which depends on the parameter A6. And now I say, is there a value of A6 that would give good data when I compare to numerical relativity? Okay? And this is what we did with Alessandro Naga, and separately Alessandra did similar work. And the answer, which is not evidently yes, actually was yes. That is to say, you can find a value of this coefficient, which after resummation gives now a very good agreement between something that you compute purely analytically, but with some information, calibrated. So this you extract as a function of the numerical simulations, but once you use it, you are analytical again, okay? So this is the idea of the EOB, where you start purely analytical. You trust something because it looks better than ordinary perturbation theory was bad, but it was like a bet, that nobody believed us, okay? Especially the people who spent a lot of money on numerical relativity, saying we will have very complicated things that merger, okay? Actually, it was, maybe we were lucky. And today, people in the group of Alessandra and young people here from the Torino group, they continue developing, improving EUB by this type of, let's say, strategy as a general thing.
Thank you. Tomorrow, I hope we keep this discussion. Now we have time for questions. I have a couple of questions.
Yes, please.
Okay, so you said at some point at the beginning of the discussion, practically, that you follow Wheeler, which said that quantum mechanics teaches, in particular, the Bohr-Sommerfeld quantization. I'm sure he had something in mind. I wanted to give so I want some example of this point. I tell you the example I know. The example I know is the relativistic correction to Schrödinger equation to the hydrogen atom that actually Bohr-Sommerfeld gives a correction as Dirac equation gives with the Bohr-Sommerfeld approach. Okay, so but I want to know Wheeler in particular what he was thinking about when he said that.
I think that what he had mainly, although he did say this as a general statement, he had mainly what he learned from his student Feynman, which is that the
Oh, a stupid one, Feynman student. A stupid student, Feynman.
yes, that you know, when Feynman wrote the path integral, and then understood that the old result of Lagrange from Torino, that you must minimize the action, although it was first done by Hamilton actually, but from the quantum mechanics, you understand that you have a phase, and you must make the sum of all the phase, so it's the Heurens principle. And then the maximum thing in the small h-bar limit will be defined by the maximum phase, the stationary phase. So he said this explicitly, that this is an example where, you know, the principle of least action was a big mystery. How come you must go to minimum? Why, if you think it's a wave, and then indeed they cancel except for this. So he had this clearly in mind.
The minimal action is the answer.
No, but then he also said explicitly that quantum mechanics help to, and there are many other examples. When you think quantum mechanically, it's often simpler, conceptually, not to solve everything. And in this case, it was, okay?
So
just to set the problem, you know, saying, because if you say, oh, this problem is equivalent to this, you can look at that and see, what do I do now? Why, if you think of the states, it's evident you must identify the idea of the action variables.
And also here, somewhat, I have the feeling that when you use the Padé at the 3 pn, by the way, yes. I don't know pn, what does it mean?
Post-Newtonian, sorry.
So why Padé approximation or another resummation? Though at the end it turned out to be right, okay? So,
yes.
For some analytic behavior that you know it must have.
For the reason I said, which was a requirement, okay? You want continuity.
Yeah, that's
continuity. So you don't want that suddenly something gives something completely different. But this was a guess, okay? But you also know that you cannot trust this expansion anyway, because all the terms become comparable, you know, +1 -1 +1. So you have to do something.
Yeah, it's an analytic a good analytic continuation.
But it is true that, you know, when you don't know how to resum, Padé is the by default thing. You have a Taylor expansion, 1 + x + x squared. If you don't know what to do in the complex plane, you say, let's try some Padé near the diagonal, except that here you were putting away from the diagonal to keep some information. In particle physics, Padé is used all the time.
Yeah. I know another example. Padé is equal holographic principle.
Yeah. Holographic was not, we did not invent the holographic principle. Okay.
More questions? Yeah, please. Yeah, you can speak and then repeat. Oh.
Yes.
Now that map also shows up in scattering systems when now the energy becomes a Lorentz factor and something. With 25 years of hindsight, how could you have
No, it's better you come here because
yes. But I can repeat the question, okay?
If you can repeat the question.
Yes. So, yes, the question is about, initially, okay, we said we don't know what is the map between the effective energy and the real energy. So we said, okay, let's write the most general perturbation expansion. And then at 1 pn, you find that this is this. But before even going, and at 2 pn also, but before that, maybe you forgot or you don't know, I had a previous paper where I had said, this is the good energy map to use anyway. And there was a paper of Itzikson, Brezin, Jean-Justin, where they said, this looks like a good map, okay? So this map was already in the air, okay? And when we found it true at 1 pn, 2 pn, 3 pn, 4 pn, we had little doubt that it was true to all others. And then I have proven in 2016 indeed, that by using what I will talk about next time, post-Minkowskian and not post-Newtonian approach, scattering approach, that it must be this map immediately, even at the first order in G, okay? That it is exact, this map, okay? So there are good reasons for this map to be the good one. No, but the fact that this is gamma, okay, we will discuss that. This is trivial. Although I remember when I found, it's just gamma, I said, it's a bit surprising. It's simple, okay? It is a very simple thing, finally, this map.
More questions?
Yes. Good point. When you are...
No, sorry.
Yes, why here? You have the frequency, orbital frequency, then it goes to a maximum, and then after the maximum, it has a sharp going down. When you are here, it's like an effective black hole that you have. It looks like a deformation of Schwarzschild black hole. For a Schwarzschild black hole, what happens is when you get very near the horizon, time slows down very much. And then, it takes an infinite time to go to the horizon. And because of this, the orbital frequency it's exponentially going to zero. It's for this fact. So it was a transition between something like this and something black hole dominated. Okay.
You have spoken about two black holes.
Yes.
But if one has one black hole and some other thing?
Yes, so indeed, I was speaking about... Yes. The effective one-body formalism is not at all limited to two black holes. It was invented with this in mind. And to predict this, you need two black holes. This is the prediction for this. But then it can be applied for two neutron stars, and we did apply it, okay, in particular with Alessandro Naga and Sebastiano Bernuzzi. When you have two neutron stars, there are two differences in the sense that when they get closer, you need to add tidal terms, which change the A function. So you need to add terms due to the tidal now attraction, because why here I was saying these terms, because they have a plus, they are repulsive in a sense, or less attractive than -1/r. When you have tidal forces, they give a minus u to the 6, something more attractive. And when they really touch, the EOB cannot tell you what happens when two neutron stars, merge, because nobody actually knows the physics there. So, but EOB can predict up to the merger, and the merger is beyond 1,000 hertz, and actually it is in the noise of LIGO-Virgo. So the signal of binary neutron stars is more important for the very long period before, where you have many cycles, because you start at, the merger is at 1 kilohertz, while the merger of two black holes of 10 or 20 solar mass is at 100 hertz. So as the LIGO-Virgo sensitive region is around between 100 and 200 hertz, you are very sensitive to the merger of black holes and you see the ring down. While for neutron star, you are sensitive to what happens before they touch. And the interesting physics thing when the two neutron stars start doing something is for the moment lost in the noise, just for you to. But EOB is quite useful to resum the thing. Okay.
More question?
On this thing with the noise, can LISA help to maybe find these things we want from neutron star merger?
So LISA now is a completely different energy. You mean for black holes, for neutron stars? I mean, LISA will be, okay, for this type of black holes, LISA will be sensitive to what happens much earlier, okay? And will predict to LIGO-Virgo saying, we have seen something here, and in a few months or in a few years, they should merge, okay? So it's a complementary thing. And if you go very early, EOB is less. I mean, EOB is useful if you want to keep track of the phase when the thing gets slightly relativistic. If you are very non-relativistic, perturbation theory should be okay. So you don't need maybe the power of resummation for, it depends. But LISA will hopefully also observe the merger of two supermassive black holes. And also very importantly, what happens when a small black hole or a neutron star falls into a big black hole. And EOB can also be useful here because EOB is beyond the probe limit. So it is like cell force effects are included. All the terms that are proportional to nu is 0 in the probe limit. So in the probe limit, everything here disappears and you have 1 minus 2u. So EOB is using already 1 SF and 2 SF effects, and therefore I think will be useful also for LISA sources.
More question? Yeah.
Just if you can repeat what you said before, that one usually tries to use a diagonal pade, but for the A potential you use 1,5. Like, is there a specific reasoning, or does it just work better?
So, yes. So first, it's not a theorem, but if you open books about pade, there are, okay, if you have a Taylor expansion, 1 plus C1x plus C2 x squared plus C3 x cubed plus C4 x4 and things like that, and the coefficients, you know, are of the same order of magnitude somewhere. It is a folklore that if the pade are parameterized by 2 integers, n and m, such that n plus m is your order of approximation, that there are theorems saying that for some functions in the complex plane, when you are near the diagonal, if you don't know anything else, it's good to use near diagonal pade. But in this case, we wanted a function which had which was close to 1 minus 2u to have a 0 somewhere. And therefore, it looked natural to put 1 plus u at the top, 1 plus a coefficient times u, to be close to this. But actually, P33 work in some cases better than P15. So at this stage, this was a guess at the time, okay? Today, you say, we have numerical relativity, we want some resummation to be good. Let's try what is the best pade now experimentally. And in some cases, Alessandro prefers P33, no? And with our young colleagues, we tried all pades, saying, the problem with pades also is that if you start with an expansion like that, you replace it by a rational function. Often you have spurious poles, that is to say, this rational function contains poles somewhere, and they make a mess. And therefore, you should avoid poles, even if this is the pade you wanted. Okay. It's like a black art, okay, after a while. Okay.
More question? I have just a curiosity. Did you realize right away that in the case of coalescence of black holes, you could be detecting the gravitational waves?
That we could what, predict, or did they
You predicted, I'm sure.
Yes.
And these could be detectable.
Yes, at the time we had this clearly in mind. Okay,
So
I had no idea of the real time scales because people. I mean, I had been in contacts with Rewise, with Driver for years, with Keep also. So I knew the detectors were improving all the time. Nobody knew whether they existed big black holes like 30 solar mass, but people expected 10 or 15 solar mass. And
actually,
we
people tell me that there were counter evidence for big black holes because they are not metals they couldn't see metals in the sky, so that there was counter evidence for large black holes.
At the time, so this was in 2000, okay, I did expect that one day we will see black holes and that we were hoping this would contribute to helping their detection. I was not aware of the fact that the Polish group had predicted that the first black holes to be detected by LIGO Virgo would have 30 solar mass up to 80 solar mass, which actually turns out to be because of metallicity thing. It seems to me that all those discussions, metallic, non-metallic big black holes, they are not based really on facts, but on prejudices that some people believe, yes, no, what you say is wrong, what I say is correct, and things like that. Nature has talked. We see these black holes. EOB is useful in this context. I'm happy.
Let's thank again for this beautiful lecture. So tomorrow, same hour, same start, right? Yes.
So the fact that we impose that A as a zero function, so we saw that B with a function which goes to zero. And then, we will need the scattering. No, Lorentz is not here, but in the scattering thing, the Lorentz transformation coming. Yeah, here it's really strong field. EOB interpolates between this field and this field.
Ciao, Gianni.
But here, then indeed we say this function.
Allora domani mi metti ancora come prendete? Come
Io no, mo glielo dico, ci vediamo domani a che ora vuole lui mi fa sapere.
Solving particle falling into the hole where you know that it goes down at the right direction. But it's not a real right because it is interaction energy of two black holes like that. It's not, but still they stay there.
Huh?
It's something you assume. It's true that nobody in America believes that because they show that objectively, there was reasoning saying but don't hope that this was a good approximation. But I could not show slightly when you see numerical relativity simulation of two black holes, what is striking is you see the two black holes, they are essentially circular, and then really in very small time, they become, you know, it's not that they start becoming jelly or whatever, or complicated space-time. The two black holes merge and become one black hole immediately. So our approximation jump sharply from two masses with this effective description. Yes. Again.
Tomorrow you will let me know what time you want to leave, okay?
Let's say the same time.
Quarter to 10. Or 9:30. 9:30.
9:30 in case we
okay.
yes, I did not. I should have written. Yes, I should. Yes, sorry, I didn't. Let me write it for you because indeed it's a very simple thing. But I wanted to write it. This equation are very simple. I take G00, which is minus 1 over the inverse of times C0 squared. But this 0 then I have R squared use an Hamiltonian in this form, all this is lost, you know, it depends on how you write even the thing. Why here we say, no, I see things, so it gave us confidence, we were seeing things, we would be the key. But one has to try things also.
Well, I guess more of a, from your perspective, when you were starting out with the formulas, like when did you, like you said, you kind of like took a chance on it, you had confidence in what you're kind of work out. When did, in part of the calculation, when did you like think, okay, this is definitely going to work? At what point?
First, we have two papers with Alessandra in 99 purely on the Hamiltonian. And I remember that there we were not ambitious at this point, okay? And we said probably COP can predict things up to the last stable system. And then we will give initial conditions for numerical relativity because at the time it was very difficult to start far away, and we said, EOB gives a good starting point, already closed.
Yeah.
Okay. And in between this and 2000, where the important point was when we computed PR square during the formula, okay, during what people call the plunge, we found that the PR square was 0.1. So it looked like indeed we could trust the formalism even beyond now the light range up to the merger. And I don't know at which stage, I mean, it's not that we said, you know, we firmly predict the signal will be this, but still we said we think the signal will be this.
Okay.
And what I remember is when I worked with Alessandro, and we had the first numerical relativity simulation that from Luciano Rettola that we could work on.
Yeah.
It was still surprising that this thing was extremely close to, okay, because what, you know, when you put the quasi-normal mode, this thing continues like that. Okay? And at this stage, the frequency change was extremely near really the NR1. So over the years, one gained more confidence, you know. It's a process.
Yeah, okay.
The computation of Alessandro on the test mass limit also helped a lot. Our first paper with Alessandro, like high accuracy waveform in the test mass limit, was using an EOB, which is something, and simulations of a test particle, where we had the waveform and things like that, and we were very close. We could predict this and say, so we gained confidence from there in 2007, and then, okay. Then there was the paper of Bonanno-Cook-Pretorius, which was the first comparison between the first NR simulation and EOB, purely analytical EOB. And in there, there was a nice agreement, okay? So all this little by little pushed in the direction where why not this?
Okay.
It was a slow process.
Okay, yeah.
It's not that one moment we said yes.
Okay, got it. And then another quick question, if you have time. So these like the A6 term and a couple other terms are the calibration terms that they use to make it more accurate to
NR.
NR. But when you
which, by the way, was something that was in my earlier paper of 96 or 98.
Okay.
Because I had worked in France with numerical relativity people. We had an approximation of two black holes by truncating Einstein's equations in some way. And we already said we can use NR simulation to calibrate things, and we can get parameters, and all that was, in my mind, quite clear before that I knew NR could do this. Alas, the French people did not get good Berger simulation, so then we worked with other people.
All right, and that but for like you're talking about the perturbation, like high mass ratio limits. There's not going to be that too many simulations. They're not going to be too long either. So what is the EOB model to calibrate for like that very long? Does it use like a self force type?
You mean calibration when U is small?
Yeah.
whether we can. Each time we said, for instance, here, we said, can we get this coefficient by very long simulation when they are far apart? Can we extract it numerically? We could never. Okay. Either nu is too small. There is a nu in front of everybody here. So this term, they all disappear in the Christmas limit.
Okay.
If we are really in the first order in nu, we computed to very high order. We computed A6, A7, A8, A9, A19. Then people push to A22.
Okay.
So the linear in nu, we compute to very high order from self-force computations. Okay.
Okay.
So which is another thing. Yes.
Right. Okay.
But I was always frustrated in the sense that it was never possible to use NR by saying, okay, let's compute the A function, NR like this. Really, what is its shape?
Yeah. Well, one thing that I'm working with Sebastiano is we're trying to basically they let A6 basically be a free parameter, so we're trying to use real data. Well, simulated real data. It will probably take really high SNRs. So basically, use real signals to calibrate A6. Is kind of the idea. Instead of using NR, just use real. Like once.
But what do you mean? Real signals.
Yeah. Like we're expecting like maybe this beam might be possible for like Cosmic Explorer or Einstein telescope, and so you could actually calibrate like some of these calibration parameters with real signals instead of using NR simulations.
But would not, it's very good, it's fantastic, but still can I say that NR is simpler to use, it's very accurate.
Well, yeah.
Conceptually it's nice to extract from.
Well, but there is a limit, right? Because the NR resolutions are only like, some papers by like Deirdre Shoemaker and others have shown that, for the next generation detectors, a lot of these NR simulations don't have high enough accuracy for the signal that we're expecting to see in the next generation.
Are you saying the real signal will be more accurate than simulation? There will be noise always.
You need more accurate simulations for how high SNR that we'll see, basically. So the systematic errors in the NR, which therefore the models are calibrated to, will be significantly, like you'll bias our answer pretty significant. So that's why like a lot of the, there's like the SXS group is working on the Spectre code, and then the Einstein group of people are working on improvements to kind of, because the problem is that the NR is limited by how long they're taking already, but the resolution that they're using is not good enough. So they're having to improve the speeds of their code so they can gain higher resolutions with the same time scale.
But evidently you have to remember here we say the A potential, but in the right hand side we put this, which is resummed in UB by Vision. But actually there are calibration parameters also here if you want, and it's the sum of this and this, so you cannot say this is determining, becomes mixed.
Right. Yeah.
But it would be good to have.
It would be interesting to like just calibrate it to real data. I wonder if that's possible.
It is quite interesting.
Yeah.
A me mi chiudi che poi deve venire...
Sta ancora aperto il microfono.
Sta ancora registrando.